And the math professor is on the air once more. Okay, well, this is a turn up for the books. I'm here in the classroom by myself. Admittedly, this is not the largest class I have. And today we're going to start on chapter 20, Quality Programs for Manufacturing. Right, so we have these 7 sections in chapter 20. Our quality control systems. This shows how it fits in our overall manufacturing program.
Welcome to Zoom. Enter your meeting ID, public. Enter your participant ID, followed. You are in the meeting now. There are 2 participants in the meeting.
If there are 2 participants in the meeting, then I'm both of them. All right, wow, that's exciting. All right, finally. So, this shows how our quality control systems fit into the overall production scheme. All right, so when we think about quality, there are 2 aspects. One is the product features, that's characteristics resulting from the design. Our functional and aesthetic features, and the grade or quality level. The second aspect is freedom from defects. That is to say, the product does what it's supposed to do and has no deficiencies or out of tolerance conditions. All right, so when we talk about those two aspects, the product features can be the design configuration, the size, weight, the function and performance, the distinguishing features of the model that we're talking about, the aesthetic appeal, ease of use, availability of options, reliability and dependability, durability and long service life, serviceability, and of course the reputation of the product and the producer. When we talk about freedom from deficiencies, that's absence of defects, conformance to specifications, the components being within tolerance, no missing parts or early failures. All right, so within the quality responsibilities, our product features are the aspect of quality that the design department is responsible for. So product features determine to a large degree the price that a company charges for its products. Freedom from deficiencies is the quality aspect for which the manufacturing departments are responsible. So our ability to minimize these defects has an important influence on the cost of the product. Of course, these are very general aspects of this. Our responsibility for high quality extends well beyond the design and manufacturing departments. So, in traditional quality control, we have a widespread use of statistical quality control. By using that, we infer the quality of the population of manufactured parts and products based on samples. So we have two principal sampling methods in statistical quality control. One is control charts. Those are graphical representations that we use to track the measured variable of interest over time. And the second is acceptance sampling. So if a sample passes, the batch is accepted. So our typical management principles and practices within this are that customers are external to the organization. The sales and marketing departments are responsible for customers. That the company is organized by functional departments, that an inspection department is responsible for quality, inspection follows the production, and that knowledge of statistical quality control techniques resides only in the minds of the QC experts in the organization. I would say this is a very old-fashioned way of looking at things. They do say it's traditional quality control practice. But within lean production, of course, we know that our customer is not just the ultimate customer, but the person at the next workstation. Okay, finally, the modern view of quality control. High quality is achieved by a combination of good management, three objectives of total quality management are achieving customer satisfaction, continuous improvement, and encouraging involvement of the entire workforce. And good technology. Using the traditional statistical tools combined with modern measurement and inspection technologies. All right, total quality management. The typical management principles and practices within that. First, quality is focused on customer satisfaction, and that is for both internal customers and external customers. Second, quality goals are driven by top management. Third, quality control is pervasive in the organization. Fourth, quality must be built into the product, not inspected in afterwards. And as a corollary to that, that production workers must inspect their own work. And fifth, that continuous improvement is a never-ending chase to design and produce better products. Okay, of course the enemy of the industrial engineer is always variation or variability. In this case, we're talking about process variability. Our manufacturing process variations come in two types. First, random variations that result from the variability built into the process. So the process is operating normally, but we have human variation from cycle to cycle, minor variations in starting materials, machine vibration, etc. Second, we have assignable variations. These indicate an exception from our normal operating conditions. So those could be operator errors, defective raw materials, tool failures, equipment malfunctions, things of this nature. All right, so these are the values of part characteristics at 4 different times during the process operation. The first one, and I don't know if you can see that timeline, the timeline here, we have the bell curve, we have our initial mean, and our initial standard deviation. Then at time 1, we have a different, where is the cursor? Cursor. All right, there's the cursor. We have our mean sub 1, our standard deviation sub 1 for the value of at time 1. At time 2, we have a different bell curve, mean sub 2, which in this case they're saying is equal to our initial mean and a standard deviation at 2, and finally at 3 we have a mean sub 3, a standard deviation 3 here. So our the mean varies at different times, I guess is the best way to describe that. When we talk about process capability, we have the equation process capability equals mu, or the process mean, plus 3 times plus or minus the standard deviation. So PC is process capability, mu is process mean, at a nominal value for the correct parameter of interest, and sigma equals the standard deviation of the process. Our assumptions are that our output is normally distributed, that we have a steady state operation, and that our process is in statistical control. Our process capability is going to have tolerance limits. So our natural tolerance limits, when the tolerance is set, is going to be equal to the process capability. Our process capability index, often known as PCK or PCI, is our upper tolerance level minus our lower tolerance level divided by 6 sigma, or 6 times the standard deviation. So that's where PCI equals process capability index. UTL and LTL are upper and lower tolerance limits, and 6 sigma is the range of natural tolerance limits. Our statistical process control, that's where we are using different methods to measure and analyze the process, either in manufacturing or non-manufacturing circumstances. So the objectives of statistical process control: well, first of all, improve the quality of our process output. Second, reduce the process variability and achieve process stability. And third is to solve processing problems. All right, so we use 7 different tools in statistical process control. sometimes referred to as the Magnificent Seven. I never heard them referred to that way, but carry on. The first is control charts. Control charts are very useful in showing us when we are getting closer to making an error. Histograms are often used to show the spread, the distribution of our measurements. Pareto charts for prioritizing quality improvement. Check sheets. Check sheets can be used to avoid errors or to discover where errors are happening. Defect concentration diagrams, scatter diagrams, and cause and effect diagrams. So control charts are a graphical technique where our statistics computed from the measured values of the process characteristic are plotted over time to determine if the process is in statistical control. So the underlying principle is that the variations in the process are from the two categories we discussed before: random variations or assignable variations. Here we see a control chart. We have the center line or mean of the process, and then we have tolerance control limits that are plus and minus 3 standard deviations from our center. All right, so here we can see, as we're measuring each of these, that we are well within our control limits. All right, so we have two basic types of control charts. We have control charts for variables. Those are where we are taking measurements of a specific quality characteristic that is of interest. So we can have an X bar chart or an R chart in this type, right? So that specific measurement will be a critical measurement for the product or part, such as diameter, length, etc. Second is control chart for attributes. Those require a determination of the fraction of defects in the sample or the number of defects in the sample. And those can be either a P chart or a C chart. All right, so here we go with an X bar chart in type A, where it measures, we take a sample, we average the measurements, and we record that for each one. So sample number 1 right there, sample number 2, number 3, and so on down the line. In an R chart, we measure the range of the deviations. So here we see a typical R chart. well, I say typical. All right, so when we interpret the control charts, the thing that tips us off most often is when the sample mean or the range are outside of the upper control limit or the lower control limit. We can also look for these other signs, trends or cyclic patterns in the data. In other words, it's trending too close to one or another of the control limits. Or maybe there is a cyclic pattern that we're worried about causing a problem. Sudden changes in average values may indicate that an adjustment or a tool is not in a good place. Having points that are consistently near the upper or lower control limits, bad sign. 8 consecutive points that lie on one side of the control limit. Boy, I don't know if I'd even wait for 8 before I started panicking a little bit. 6 consecutive points in which each point is higher or lower than its predecessor. Again, that goes back to the trends. When we see that we are apparently on a trend, we need to check and see what's going on. All right, so our control chart used as a feedback loop in our statistical process control. All right, so we have our inputs, then that goes into the process. Our process output goes out, but we have a measurement that goes onto the control chart. If the process is in statistical control, we take no action. If it's out of control, we identify the cause and take corrective action. All right, so a histogram is a statistical graph consisting of bars representing different members of a population in which the length of each bar indicates the frequency or relative frequency of each member. Okay, great. It's a very useful tool for visualizing the shape of the statistical distribution. So the shape of the distribution, the central tendency of the distribution, approximations of our mean and mode in the distribution, and the amount of scatter or variability in the data. All right, so here we see a histogram of our process, right? And we can see, all right, if 2.000 is the mean that we're shooting for, then we're not doing too bad. Everything is pretty close to there. All right, so a Pareto chart is a special form of histogram where our attribute data is arranged according to some criteria. That could be cost, it could be value. It's based on Pareto's law. Pareto, of course, the Italian mathematician. We often will call this the 80-20 rule. The examples they give are 80% of the nation's wealth is owned by 20% of the population. 80% of sales are accounted for by 20% of the stock keeping units. Or for that matter, 80% of the sales are accounted for by 20% of the salesmen. That is a somewhat famous statistic by itself. All right, so here is a Pareto chart of sales of different product models. Strange how that goes by the alphabetical order is the same as the sales, right? We could also do this and often do this for things like why are we not achieving the product quality, right? The first one might be poor machine setup, second one operator error, third tool wear, and so on. Okay, a check sheet they're defining as a data collection tool generally used in the preliminary stages of a study of a quality problem. Check sheet is also what we call a list of instructions at a workstation on checking the key points of in assembling or working on a product or part. Data often entered by worker as check marks in a given category. So a process distribution check sheet gives us data on the process variability. A defective item check sheet, types and frequencies of defects on the product. Defect location sheet, where defects are occurring on the product. We can also have the defect concentration diagram. So in this case, it's a drawing of the product onto which locations and frequencies of various defect types are added. This can be useful for analyzing the causes of product or part defects. So by analyzing defect types and corresponding locations, the underlying causes of the defects can possibly be identified. And our next, we see four views of refrigerators, right? The idea being that every time there is a defect, it is marked on one of these diagrams, and eventually we figure out what is causing those particular defects. All right, so scatter diagrams, Those are XY plots of data collected on two variables where we suspect there is a correlation between those variables. The data are plotted in pairs. For each xi value, there is a corresponding yi value. So the shape of the collection of our data points can reveal a pattern or a relationship between the variables. All right, so here we see an xy where our x-axis is the percentage of cobalt, and our wear resistance is our y, and we see that at just the right amount of cobalt, we seem to have a higher wear resistance. But too much cobalt means not as much wear resistance. We can have a cause and effect diagram. In that case, it's a graphical tabular chart used to list and analyze potential causes of a given problem. Also known as a fishbone diagram or an Ishikawa diagram. And we can use that to identify the causes that have the greatest consequences, and thus analyze how to take corrective action against them. All right, so here we see an Ishikawa diagram, or cause and effect diagram, fishbone diagram, whatever we want to call it. The effect that we get is we have poor solder joints. The different things that could go into that are the specifications, the workers, the method, the process, the equipment, and the materials. All right, so all of these have various causes associated with them. In fact, in two cases, missed soldering joints might be either the worker or the method, and inadequate training might also be the worker or the method. Otherwise, all of them are assigned to one cause. So implementing statistical process control, they associate these 5 elements with a successful statistical process control program. One is management, commitment, and leadership. In fact, for almost anything to be successful, we need that. So our management is setting the example for us all to follow. Second is a team approach to problem solving. So the different team members contribute because they have a broad pool of knowledge between them. Third, statistical process control training for all employees. So usually, I've seen that more confined to the people who work on the shop floor, but the more people that know, the better. Emphasis on continuous improvement throughout the organization. That is something I believe in heavily. A recognition and communication system to recognize successful SPC efforts. So, of course, we always want recognition of people doing the right thing and transparency and communication. All right, so when we talk about a Six Sigma program, that's a quality-focused program that utilizes worker teams to accomplish projects aimed at improving an organization's operational performance. So the big pictures, goals of a Six Sigma program: better customer satisfaction, high quality products and services, reduced defects, improved process capability, continuous improvement, and cost reduction by more effective and efficient processes. All right, so in this case, a Six Sigma program brings us quality based on the normal distribution. The traditional metric for a good process quality is plus or minus 3 standard deviations, or sigmas. So that is going to include 99.73% of the population. That means that the defect rate is going to equal 27 defects per million. 2,700 defects per million. So our Six Sigma metric is plus or minus 6 sigma. May I help you, ma'am? I'm over here behind the screen.
Screen. What screen? Okay.
Are you looking for someone?
Yeah, Cheryl's the one that's supposed to do my pets.
Okay, you actually want room 316, but I don't believe they're doing taxes this year.
Well, I called her and she said she was gonna do it, but then after I called her back and she wasn't in here all this time, so I thought I would just come in and talk to her, but it looks like that her office is closed.
Not very many people are here. In fact, I'm only here because I'm doing a class right now.
Oh,
So, but if they're not in room 316, I'm sorry, I don't know what to tell you.
oh gosh. Cheryl. Her name is Cheryl, huh?
I don't know. Usually it's Tilda Woody that is in charge of doing the taxes.
Is she here though?
I
Somewhere?
don't know. I don't think so.
Where is the main office at?
The main office for the school
Uh-huh.
would be in the Empowerment Building.
Empowerment?
Yeah, the building that looks like it has wings.
Uh-huh.
That's the one.
Oh, gosh. I wonder if someone can help me. Where's this guy at?
He went to the business office, I believe.
Just now?
Yes.
Yeah, he's the one that, is thinking that, he's working with Cheryl.
Maybe. You have me there. So sorry I can't help.
I know. It's like that, just like winter rock. I don't know. Go check this building.
Okay,
Office
well,
number.
so sorry.
Nobody answers. Thank you.
Not a problem. All right. So our Six Sigma metric is plus or minus 6 sigma, or plus or minus 6 standard deviations. In our standard normal tables, that would include 99.9999998% of the population. Or our defect rate then would be 0.02002 defects per million. All right, so plus or minus 3 sigma in our normal distribution means that here we have our minus 3 sigmas, or 3 standard deviations. Here we have our plus 3 standard deviations. And that takes in 99.73% of everything. Plus or minus 6 sigma in our normal distribution means that that would go from minus 6 sigma to positive 6 sigma. Although you'll notice for our purposes, the diagram only goes to plus or minus 4 sigmas. So at a sigma level of 6 sigma, our defects per million are 3.4. And on down through here, I think it's kind of pointless to read you this diagram. Unfortunately, it doesn't say what diagram it is in the book. And here it keeps coming down until we get to 1 standard deviation, or 1 sigma. All right, so 6 sigma was originally invented by engineers at Motorola. And they said, we are only going to think about processes that operate over a long run. Over that long run, our process mean will shift. So to compensate, Motorola decided to use 1.5 standard deviations as the magnitude of the shift. So 6 sigma is really 4.5 sigmas. Here they're illustrating that shift of 1.5 standard deviations. So we have our normal distribution, and then we have our shifted distribution. So our statistical process of Six Sigma is paired with an iterative process for improvement. The first step is define. We define our project goals, our customer requirements, and what we're going to measure. Second, we measure the process and assess the current performance. Third is we analyze the process and determine the root cause of variations and defects that arise from it. The fourth is we improve the process, trying to eliminate those root causes. And then 5 is we control. We have control over the improved process to eliminate those root causes for variations and defects. So this is known as the DMAIC procedure. All right, so we think of our measures of defects by the millions. So first off, there are defects per million opportunities. So it's 1 million times the fractional quality of the number of defects divided by the product of the number of units times the number of opportunities for a defect per unit. Then we talk about defects per million. In that case, it's 1 million times the number of defects divided by the number of units. Then we talk about defective units per million, or DUPM, which is 1 million times the number of defective units divided by the number of units. All right, so in this example, we have a manufactured product, unspecified as to what it is. We have features that are considered critical to quality, and there are 37 of them. We produce 31,487 of the products, of which 1,690 had defects of the critical to quality features. The products that had one or more defects are 902. So therefore, the number of opportunities is 37. The number of units is 31,487. The number of defects is 1,690, and the number of defective units is 902. Therefore, the defects per million opportunities is 1 million times 1,690 divided by the product of 31,487 times 37 is equal to 1,451. That puts it at a sigma level of 4.5. The defects per million equals 1 million times 1,690 units, 90 defects divided by 31,487 for 53,673, putting it at a sigma level of 3.1. The defective units per millions equals 1 million times 902 divided by 31,487 equals 28,647 for a sigma level of 3.4. No doubt you're riveted by these numbers. All right, so Taguchi methods in quality engineering. Well, first of all, quality engineering is a broad range of engineering and operational activities whose aim is to ensure that a product's quality characteristics are at their nominal or target values. So it has a lot in common with total quality management. The Taguchi methods are using robust design and the Taguchi loss function. So when we talk about robust design, first of all, there are noise factors. These are sources of variation that are impossible or difficult to control and that affect the functional characteristics of the product. So, the types of noise factors, we might have unit-to-unit noise factors. Those are random variations caused by variability in materials, machinery, or human participation. We have internal noise factors that can be, one, time-dependent factors such as wear or spoilage. Two, operational errors such as improper machine settings. And then we can have three external noise factors. Those are things like outside temperature, humidity, input voltage. So a robust design is a design in which the function and performance of the product or process are relatively insensitive to variations in any of the noise factors. In product design, robustness means that the product performs consistently despite disturbances and variations in operating environment. In process design, robustness means that the process continues to produce good product despite disturbances and variations in the operating environment. All right, so some examples of robust product design. The first is an airplane that flies in stormy weather as well as in clear weather. A car that starts in Minneapolis in January as well as in Phoenix in July. A tennis racket that returns a ball just as well when hit near the rim as when hit dead center. And our fourth example is a hospital operating room that maintains lighting and life support systems when electric power to the hospital is interrupted. Could be kind of important. More examples. A machining operation that produces good surface finish throughout a wide range of cutting speeds. A plastic molding operation that molds good parts despite variations in ambient temperature and humidity in the plant. A metal forging operation that presses good parts despite variations in starting temperature of the raw billet. All right, so that brings us to the other part of the Taguchi method, which is the Taguchi loss function. According to Taguchi, quality is the loss a product costs society from the time the product is released for shipment. So our loss includes the cost to operate, failure to function, maintenance and repair cost, customer dissatisfaction, and injuries caused by poor design. Defective products or their components that are detected, repaired, reworked prior to shipment are manufacturing costs. Okay, so there you have it. So loss occurs when the product's functional characteristics are different than the nominal or target values. When the dimension of a component differs from its nominal value, the component's function is adversely affected. As that deviation increases, the loss increases at an accelerating rate. This viewpoint differs from the traditional quality control approach, which defines upper and lower tolerance limits, and that anything in between is acceptable. Okay, so with a quadratic equation, the quality loss function is, yes ma'am, may I help you?
Yeah, do you know where the income, the file, the income tax?
The interns,
You told us the rate of income tax.
I'm sorry ma'am, I have no idea where that is.
They used to be the first one, I don't know.
I would try room 316. Okay, so we have our loss, which is our, on the y-axis against an x-axis here. So nominally, all of this gray area is loss with scrap or rework cost, and in between the lower tolerance limit and the upper tolerance limit is where we want to be, of course. Rapidly shifting gears, we'll talk about the ISO 9000 standard. ISO is the International Organization for Standardization, although you would think that would be iOS. Usually in the US, we call it the International Standards Organization. ISO 9000 is just the kind of standard way we talk about this. For example, I helped with the ISO process at the Corpus Christi Army Depot, where they were given an ISO 14010 rating because of the work that they do. Our U.S. representative is the ANSI well, I'm not even sure how you're supposed to say that. I believe that means the American National Standards Institute and the American Society for Quality Control. So this is a standard for systems and procedures that are used by a facility that affect the quality of the products and services provided by the facility. So it is not a standard for the products and services themselves, just for the methods and procedures used to create those. So it's generic, not industry specific. Right? It can be applied to any facility producing any product or providing any service. So, for example, at the Corpus Christi Army Depot, we were doing MRO work on helicopters, that is to say maintenance, repair, and overhaul, and we got a specific aircraft ISO label of ISO 14010. All right, so there are two ways or two reasons we might apply the ISO 9000 standard. The first is we might implement those standards so that we can improve our firm's quality systems. The second is we might actually want to be ISO 9000 registered. So that is a formal certification that satisfies the standards, and the benefits from that are reducing the frequency of quality audits by customer firms, and to qualify for business partnerships with companies that require that ISO 9000 registration. Let me remind you that everything you've seen today is copyrighted. So don't even attempt to reproduce it in any way, shape, or form without the permission of the authors. Okay, any questions? I'm going to call that no questions. Okay, well, then that's it for today's class, and we will meet at 2 o'clock on Wednesday, and we will proceed from there. In the meantime, happy trails to you until we meet again. Happy trails to you. Keep smiling until then. It really doesn't matter what the weather. We'll get along just fine if we're together. Oh, happy trails to you.